today I will tell you something about how we do personalized recommendations at Bloomreach. So first of all, what is Bloomreach? Maybe some of you remember a company called Exponia, which was a startup based in Bratislava. And Bloomreach acquired Exponia in the beginning of the last year. And the product of Exponia is what we now call Bloomreach Engagement. And it is basically about customer engagement in various ways. And in Bloomreach we have other products, such as Discovery, which is mainly product search. And we also have what we call Content Pillar, which is a content management system. And Bloomreach is used by more than 850 customers worldwide, and these include customers such as Puma, Marks & Spencer, or even Kiwi.com. And we are also proud to call Bloomreach a unicorn, which is a name for the company which has not yet gone public, but has a valuation of more than $1 billion. And Bloomreach has currently a valuation of $2.2 billion. So just a bit about myself. So I'm a machine learning engineer at Bloomreach, and I work mainly on the engagement pillar, although I do some work for Discovery as well. And I'm responsible for all the AI algorithms that we do on engagement pillar. And I've recently started a podcast called Now Neuronic about AI, so feel free to check it out. Yeah, just a bit of motivation for recommendation and why it makes sense to do them. So Netflix published a number that 2/3 of movies watched on Netflix come from recommendations. Also, Amazon published that 35% of their sales are coming from recommendations. We also have some numbers of our own. So for example, one of our clients, Yves Rocher, increased his purchase rate 11 times compared to just recommending a top-selling product. Also, another customer called Vitkash increased the conversion rate by 23.2% in 5 months. In engagement, we have various types of recommendation engines, and our customers can choose which one they want to use and where they want to place them on their website. There is a different algorithm behind every one of these templates, but what we will focus on in today's talk will be just personalized recommendations, which is just like one of the templates, although it's the main template. So like I will explain the basics first, and then we will go into like what we are now developing and the ongoing research. So basically, what's the main idea behind all recommender systems? Imagine we have two actors, so Homer Simpson and Peter Griffin. And we know that Homer likes, for example, pizza and donuts, and Peter Griffin also likes pizza and donuts. And therefore, we can say that Homer and Peter have a similar taste, yeah? And then we find out that Homer also likes chips. So it makes sense to recommend this product to Peter Griffin as well. So in general, we can say that we recommend similar products to similar customers. And a nice thing about this is that we can apply to any domain. Yeah? So it can be clothes, groceries, videos, flight tickets, or anything, basically. So the question is, how do we determine what is the taste of the customer? What do they like? So for this, we can use user feedback. And user feedback can be either explicit or implicit. Explicit feedback is what you just like explicitly say. So if you put like or dislike on something, if you add a product rating, for example, the stars, I'm sure you know them. The pitfall of this approach is that we have really few entries of this explicit feedback because it requires additional effort from the users, and so the data is very sparse. Therefore, what we are currently doing is to rely on implicit feedback, which is just general feedback from any user activity. So this can include events such as like product view, purchase, add to cart, listening to a song, or anything else. This way we have many entries and we can just use them to train our models. In Bloomreach, our clients can actually select any event they would like to use, so depending on their domain, for example. And they can use multiple of these events and just like assign different weights to them. So what we then do is we can build a preference matrix like this, and Basically, in rows we have our users, and in columns we have the products. So what the values in the cells mean? So if we had like explicit feedback, for example, the star ratings, the values would be just like 1 to 5. Like how many stars did the users put for the given product? If we have like implicit feedback, this value can be like a linear combination of anything. So it can be just like number of views of a product, or it can be like number of views plus 5 times number of purchases, or something like this. And we can just really use it in the same way. So in this case, we have our Homer Simpson, Peter Griffin. We also have Marek. Marek is our tech lead. Then there is also myself. So you can see that in this matrix, some of the values are missing. And the idea behind recommender system is to basically fill out these missing values and just recommend them to the users. So for example, here you can see that Marek likes chips and beer, and I like pizza and chips. And maybe the question would be, do I like beer? So we would like to get the value of this cell, just like whether it would make sense to recommend this product to me. So how do we do it? We use what is called a matrix factorization algorithm, which basically means that we factorize this matrix into 2 matrices, which when multiplied, they will reconstruct the original matrix. So we have like 2 matrices. One is user factor and other is item factor. And yeah, as I said, when you multiply them, you get the original matrix. The nice thing about this is that you don't get exactly the original matrix. What you get is some approximation of this matrix, and actually the missing values are not all zeros. So they are usually like quite low numbers, but if you just like take them and you sort them, you can use this as personalized recommendation. So for this factorization, we can use different algorithms that are available. One of the popular one is alternating least square algorithm. So I said that we get these user and item factors out of this approach. So what is nice is that these item factors or user factors have similar properties as word embeddings in natural language processing. I'm sure you know them. Like the words that appear in the same context are very close to each other, basically in NLP. And this is very similar, or similar users are just like close together in this space. For example, here you can see it. And what we can do is we can use this property of embeddings to make a prediction. So basically, we can find similar products to any product. And what we are doing is we take some user and we look at the recent interactions that he did, and we find similar items to every one of his interactions. And then we can rank them and just like serve them to him as a prediction. The nice thing about this is that you can actually pre-compute the similar products to every product. So imagine just having like a database where you have just like every product, and you have the 3 or 5 or something, the most similar products, and this just like saves the resources because you don't need to make online inference. And actually, when we did it this way, we got like 20 to 30% performance boost compared to just doing the dot product, the multiplication of item factors and user factors. So what we were doing is imagine that like Bloomreach has a lot of customers. Every customer has his own model, and this customer has like different number of products and different number of users. What this means is that this customer needs a different model, and this model needs to be like, it needs to have different hyperparameters, and therefore we would like to find them. We cannot just set the same hyperparameters for all the customers. The problem with this is that you don't want to be doing a grid search or some other technique every time the model retrains, which is happening like every night basically. But you want something like more effective. And so what we were doing is we were trying to estimate whether there is some correlation between how big the model should be and the properties of the customer. So like how many items, for example, he has. And we found it. We found that like the size of the model is basically determined by the number of factors. So the number of factors is just the hyperparameter, and it just basically means what is the dimension of the embedding. And we found this correlation that you can see here, which is just like with the increasing number of items, the model needs to be bigger, and the number of users didn't play any role, or also the sparsity didn't play any role. So we are just like using this right now to estimate the number of factors, and it also gave us 10 to 20% improvement for various clients, just comparing it to just having a fixed value for all the clients. So this is the current approach that we are using, but of course it has some pitfalls. You've probably heard about the cold start problem, which is basically a problem that when a new user comes or a new item is like introduced to the catalog, we don't have any interactions for this user or for this item. So therefore, we are unable to provide a recommendation. So what we are currently doing is we use just a basic fallback, which recommends the most popular products. But we are having a research which focuses on a so-called hybrid approach, and this means that we are not only using the interactions, but we can use the metadata of the product. So we know what is the product category, the description, we have the image of the product, and so on. And therefore, we can use this to do the recommendation. Also, for the user, we can know some like demographic features, the language that he's using, or like what is his location, which browser he's using, and so on, and we can leverage this data. So how do we do that? So there is this one architecture that is really popular right now. It's kind of like a state-of-the-art approach, which is used by eBay and other. The idea behind this architecture is that you basically have two towers. You have a user tower and an item tower, and you use like user features, you input them to the user tower, and item features to item tower. And this can be like any mix of interactions and other meta features on both sides. Then you can just add like any number of layers you want. And the last layer basically is an embedding. So the last layer is almost the same thing as the user factor or item factor that I mentioned before. What you do after that is you just like do a dot product between these two embeddings. And usually what we do is we normalize these user and item embeddings. What this means is when you normalize the vector and do a dot product, it's the same thing as cosine similarity. So it's just like a distance metric, and you just like activate the result, the one scalar that you get out of this dot product, and then you just like train the neural network in this way. Whether the user likes the item or not, so whether he like viewed it or purchased it or something. The nice thing about this is that the user embeddings and item embeddings will end up in the same space, which is basically just like a property of training it in this way, because you want to like put the users and the items close to each other when they like the item. So what you can do, like how do you actually do an inference? So you can take just like a user embedding of some user, and you find just like a nearest neighbor items to him, and that's your prediction basically. So what are like advantages of this approach? So the original approach with the metrics and metrics factorization that I mentioned, it basically used a bag of words representation of the interactions. What this means is, like, imagine that the user was like looking for a washing machine, and then he was looking for a bicycle. Now imagine a user that did it in a reverse order. Yeah, first looking for bicycle and then looking for washing machine. These two users with the bag of words representation have the same vector basically and the same embedding, which is kind of a problem because like if the user has already like bought the bicycle and now looking at washing machines, you don't want to like recommend him the bicycle and so on. So this user is just like in a different state, and we want to represent him differently. So yeah, the pack of words is just like a vector of zeros with ones for the interactive elements. And yeah, the pack of words disregards the timeline, so the recency is not taken into account. We found that this recency is really important. Even the baseline of recommending just the most recent items to the user, basically the exactly same items that he has viewed, has a very high score. So recency definitely makes sense. And so how we can do it better is we can use a recurrent neural network, the model that is often used in NLP. And we can use this network to represent the user interactions as a sequence. So imagine that the user viewed some item, that he added it to the cart, then he bought it, then he viewed some other items, and we just take this as a sequence and input it to the recurrent model and get the embedding out of it. So with the example with washing machines and bicycles, it's basically you would first input the first user, the first items, then the second items, and you would just end up with a different representation. Additionally, we can just add any other features, so for example, which browser the user is using and so on, and just put it all together, and this is the input to the user tablet. And that is basically, yeah, thank you all for your attention, and if you have any questions, feel free to ask.